welcome to the deep dive. Today, we're really unpacking some fascinating stuff.
We are.
It's all about a fundamental process in your brain, how it predicts rewards.
Yeah, the reward system.
We've got some great source material, articles, research notes, focusing on one specific area, the VTA.
The ventral tegmental area.
Exactly. And there's this surprising new discovery about something we didn't quite grasp before. How your brain handles time, like really precisely when thinking about future good things.
That's right. So our mission here is to go beyond just, predicting if a reward will happen.
Right.
The material shows a much, much richer picture. It suggests your brain predicts the precise moment it expects that reward.
Wow. Okay.
And what's really striking is how this timing aspect seems to give the brain amazing flexibility.
And AI is involved somehow. That's kind of unexpected.
It is. Artificial intelligence actually played a really key role in figuring this out.
Okay, let's rewind a bit. Before all this new research, what was the general understanding of the VTA?
Well, traditionally, the VTA was mainly known as, a core part of the brain's reward circuit.
The dopamine place.
Exactly. Its main job was thought to be producing dopamine. The idea was you get a reward, dopamine gets released, and that kind of stamps the experience as good, reinforces whatever you did to get it.
So dopamine meant, hooray, reward achieved, basically.
Pretty much.
But that view changed quite a bit, didn't it, back in the 90s?
It really did. That's when researchers started realizing the VTA wasn't just reacting after the reward. Its activity, especially those dopamine signals, seemed to be much more about the prediction of the reward. It shifted from a reward is here signal to more of an expecting reward soon signal.
Okay, and the sources mentioned that classic experiment, right? Like an animal learning a light means food is coming.
That's the perfect example. You watch the dopamine response change. At first, the dopamine spikes when the food arrives. Simple enough.
Makes sense.
But after learning the connection, the spike moves. It doesn't fire for the food anymore. It fires the moment the light comes on.
Because the light predicts the food.
Exactly. The brain responds to the prediction.
And that whole idea, learning based on predicting outcomes, that's reinforcement learning, right? Which is huge.
Absolutely fundamental. It's how we humans learn pretty efficiently without constant hand-holding. And it's also the basis for loads of powerful AI systems.
Like AlphaGo and things like that.
Precisely. The brain's knack for prediction and reward learning gave us the core ideas for those reinforcement learning algorithms. The basic concept is shared, even if the nuts and bolts are different.
Okay, so we got that the VTA predicts based on cues. But this newer research you mentioned from University of Geneva, Harvard, McGill, it takes things quite a step further.
It really does. This is where it gets incredibly detailed and, frankly, quite amazing.
So what's the big reveal?
The core finding is that the VTA isn't just giving a single general prediction about, say, the overall value of future rewards. Instead, it seems to be predicting the temporal evolution of those rewards. What's really fascinating is the idea that each potential future reward might be represented distinctly.
Separately.
Separately, yes, and crucially, tagged with the precise moment it's expected to show up.
Whoa. So it's not just like, okay, future rewards are worth X amount. It's more like the brain keeps a schedule. Small reward, 5 seconds. Bigger one, 30 seconds. Maybe something else in 5 minutes. And it knows the arrival time for each.
That's a great way to put it. It's a real departure from older models that might have just averaged everything out into one prediction signal. This suggests a much richer, time-stamped map of what's coming. It's tracking when, not just if.
And the sources talk about multi-timescale encoding. How does that fit in?
Yes, that's key to how it seems to work. They found evidence suggesting different neurons, or groups of neurons in the VTA, are basically specialists.
Specialists.
Yeah, tuned to predict rewards on different time horizons. So you might have some neurons firing mainly for rewards expected in the next few seconds. Others that are more active for rewards expected maybe a minute from now.
Right.
And potentially others looking even further into the future.
Huh. We always hear that phrase, a bird in the hand is worth 2 in the bush.
Yeah.
The sources mentioned that tendency to prefer immediate rewards. How does this multi-timescale thing relate to that?
Well, it could provide the actual brain mechanism for that bias. While we often do value immediate stuff more, this research shows how the brain constructs the detailed map of all the potential future rewards, near and far.
Oh, okay.
So it's not just one simple discount function being applied across the board. It seems to be the combined activity of these diverse neurons, each handling its own time window. This detailed map allows for focusing on the now, but also for planning for the later.
So why is this level of detail, this precise timing, so important? What does it actually do for the brain?
The argument of the sources is that this fine-grained timing information gives the whole learning system incredible flexibility.
Flexibility how?
Well, if your brain knows exactly when different rewards are expected, it can change its strategy on the fly. Depending on, say, your current goal or the situation, your brain can choose to focus on getting that immediate reward.
Right.
Or it can switch gears and decide, no, let's aim for that bigger payoff that's coming later.
Right.
This ability to flexibly weigh present versus future is just vital for complex decisions in a world where timing really matters.
And it's pretty amazing that figuring this out wasn't just about looking at neurons under a microscope. AI played a big part, as you said.
It really highlights how powerful combining fields can be. I mean, the raw data from VTA neurons is incredibly noisy and complex.
Hard to make sense of.
Very hard with traditional methods alone. So a crucial element here was a specific machine learning algorithm. Alexandre Pouget's team developed it.
Okay, and how did that collaboration work? The material mentions researchers at Harvard, too.
Right, so you had researchers like Naoshi Uchida and his group at Harvard collecting absolutely vast amounts of detailed neurophysiological data, recording what individual VTA neurons were doing.
Yeah.
That was the essential raw material.
Got it.
Then Pouget's team brought in their algorithm, which was specifically designed to sift through that complex neural activity and look for patterns that lined up with the precise timing of expected rewards.
And applying the AI to the brain data revealed the pattern.
Exactly. The algorithm could decode those complex signals and basically pull out the hidden timing information that the VTA neurons were encoding. It showed the multi-timescale predictions.
That's such a great example of that two-way street idea between neuroscience and AI that the sources talk about.
Absolutely. We often talk about how the brain inspires AI design. But this is the flip side. Advanced AI, these computational tools, can become essential instruments for neuroscience. They help us see things in brain data, really subtle, complex patterns that were practically invisible before.
So let's bring this back to you listening right now. Just think for a second about this incredibly sophisticated system running inside your own head.
Yeah, your brain is constantly running these predictions about when rewards might show up across all these different timescales.
How might that influence the choices you make every single day?
You know, when you're deciding, do I eat the cookie now or save it? Or maybe, do I finish this easy, enjoyable task or tackle that harder one that pays off later? Or even making big long-term plans. This VTA mechanism, with its really precise timing predictions, is likely humming away in the background, shaping how you weigh up immediate gratification versus those delayed rewards.
It could be a real aha moment, couldn't it? Understanding that there's this biological system finely tuned to the timing of expected good things. It gives you a new way to think about your own motivation.
Or your impulsivity, maybe.
Yeah, or your ability to be patient and stick with long-term goals.
Exactly. It helps kind of ground those very human experiences in the actual neural machinery that's constantly modeling your future, temporally speaking.
So just to quickly wrap up this deep dive, we've seen the VTA go from being understood as just a reward center to, well, a sophisticated prediction engine.
And the really big news is that it's not just predicting if, but when, using different neurons for different timescales.
Right. This multi-timescale, precise timing is crucial for flexible learning and deciding what to do next.
And AI was key to unlocking this understanding, showing that great synergy between fields.
Okay, so here's a final thought for you to mull over. We have this intricate, deeply embedded system in the brain, automatically timing future rewards, mostly beneath our conscious radar.
So how does your conscious self, the part of you that deliberately makes choices, especially when you're wrestling with wanting something now versus aiming for a bigger goal later, how does that conscious process interact with these powerful underlying temporal predictions coming from places like the VTA? Does it override them? Does it follow them? Something else entirely?